At some slides where we'll see some theoretical stuff about R. We are going to see some commands also, but we are not going to program in this lecture. If you want, you can skip it, but I would advise you to stick and just continue with this lesson and see it, because the concepts will stick more in your head and you'll have more exposure to different concepts that you'll learn in this course, okay? So let's start. So what is R? R is basically a language and an environment for statistical computing and graphics. R enables you to have a lot of statistical operations that you can do on data, such as linear and nonlinear modeling, classical tests, statistical tests, time series analysis, or even classification or clustering. So R provides you with a lot of tools to do statistical analysis and data analysis, and you can also use plots, or you can even use R as a calculator, as we will see in the next lecture. It's a really extensible and flexible software. So as you go down, the complexity is also higher. First, and the most basic usage of R is to use R as a calculator. I would assume that most of you are not in this course to use R only as a calculator. I hope that you learn more concepts than that, but it's a usage. Also, another type of thing that you can do is to compute several statistics about data and also to plot data. I think that these two are intertwined in terms of complexity. They are both of similar complexity. And then to develop machine learning algorithms, which certainly is one of the most advanced usages in R that we have. We will not learn how to develop machine learning algorithms in this course, so I'll do a course later only on developing machine learning algorithms, because I think that if you are a beginner, it might be too much information to know everything about R all at once. Most people don't need to use R to develop machine learning algorithms. They only need R to analyze data, plotting data, and do statistics about some data sets. Okay, so we can use R as a calculator, and for example, R performs most of the mathematical calculations you can think of. Everything that's in here, we are going to try later on the practical lessons. So 1 plus 2 on the console, on the R console, yields 3 as a result. 100 minus 50.6 yields 49.4, also pretty trivial. Now, R has also some special functions that compute well-known mathematical operations, such as square roots, exponentials, or logarithms, as you can see here. For example, you can perform complex calculations that obey to mathematical rules. 10 over 10 is 1, 5 over 5 is 1, 1 over 1 is 1. So R also respects the parentheses rule in mathematical expressions. You can call the exponential of 0, which is 1, times 20, which gives 20 and yields 20 as a result. You can also combine several functions one inside the other. For example, you can do square root of 9, which will be 3, and then evaluate the 3 at the exponential, which yields 20.08554. So here we are doing a kind of composite function, okay? So most of the stuff that we use in R are objects. Objects are things that we develop and store using calculations or other types of things, data, for example, that we want to store. These objects are characterized basically by two things: their own characteristics, size, dimensions, data types, and etc., and their own set of functions, things that you can call on the object and apply it to. For example, if you have a table that has a column with the name of the students of your class, that column will have a data type of string, because there are letters and characters basically that represent the name of the student, and the size of that column will be the number of students that you have. And you can call a lot of things on this object. For example, you can count the number of students with a certain name, and that's a function that you can apply to that object. So here are an example of several R objects: vectors, matrices, lists, and data frames are some of the examples of the R objects that we will use throughout this course. So let's start with the most simple yet powerful object, that is the vector. The vector is characterized by the size and the type of its elements. Elements of the vector have to be of the same type. So for example, if you have number in the position 1 of the vector, everything in that vector has to be numbers. Okay, so vectors are index-based, which means that you can access an object inside that vector by its position or index. So you can create a vector with this command, which is C open close parentheses, and we are going to create here a simple example, which is the melons. Imagine if a vector is like a box of fruits of the same type. So you can create this vector melons, which is creating our box of fruits with this command, melons equals to C, and inside we can put, for example, the weight of the melons. So 3.4, 3.1, 3, and 4.5. To access the weight of melon 1, we would use melons 1, and we would get this 3.4. So I'm just going to talk a bit about the environment in R. So the environment in R is where we store our melons. So just like if we have a box of melons in our home, they will occupy some space. Also, the variables that we create occupy space in the memory of our computer. So you can assign basically objects into variables using equals or using this symbol here, less than hyphen, which is the same. This yields the same result and basically stores this vector of weights of melons in a variable called melons. And as soon as you do some assignment, basically you create this object in your environment and you can call it later. We'll see how this unfolds during the practical lessons also. So you are probably thinking, okay, now I have a vector which has the weights of each melon, but what can I do with this? Imagine that you work for a fruit shop and someone tells you, okay, this is a vector that has the weights of the melons, of 4 melons in a box that arrived from some supplier. But the supplier tells you, oh, there was a problem when weighing the melons. So the melons have only half the weight. So you normally do is simply dividing melons by 2, and this division by 2 would be applied to each one of the elements in the vector. 2 elements on index 1, 2 elements on index 2, on index 3, and on index 4. So basically you are just applying this division to every element of the vector. Okay, so imagine that the supplier tells you another problem. There was a problem when weighing the melons, so the melons have 2 times the weight that we've told you. It's not this value, but 2 times the weight. We would just multiply it by 2 and the same is done. So the 2 would be multiplied by 3.4, by 3.1, by 3, and by 4.6. We are going to see this also in the practical lectures. Now, for example, we can also do other vector operations as summing 2 vectors of the same size. If the supplier tells us there was a problem on the measurements, or you had to add these values to their weight. So the melons are incorrect, and the melon 1 has more 0.4 weight, melon 2 has more 0.2, melon 3 has more 0.4, and melon 4 has more 0.3. Well, you can create a vector with each element that we have here, like a new vector, and just sum it to our melons vector. It would add each element with each corresponding position on the new vector. So 3.4 is in position 1 in the vector melons, would be added to the value 0.4 because that's the value on the index 1, this vector that we've created. So, and so on. 3.1 would be added to 0.2, 3 would be added to 0.4, and 4.5 would be added to 0.3. So this is really handy. Here it is the result of the calculation. Basically, what we would see is a new vector with this value. So 3.8, 3.3, 3.4, and 4.3. Okay. So the cool thing is that we can make this more meaningful by calling this vector and assign it to a new variable called adjust weight. And then our calculation will just be new melons will be equal to original melons weight plus the adjust of the weight. And this would result in this vector right here. Now imagine that the supplier would do some really crazy calculations on the weights and would send you the wrong weights, but they would tell you that the value of the melon's weight is the square root of the value we gave you. So you can also apply a function with a vector as an argument. So you would say square root, sqrt, of melons, and this would weight all the square root of each of these values. So just like the division by 2 was applied to each element on the vector, so was the square root was going to be applied, so would be the exponential, so would be the logarithm. Every function or mathematical function that you can think of would be applied to each element. So imagine that your boss now would weight, well, please sum the total weights of the melons in that box, which is our vector, and we can just call sum melons, and that would yield 14, which is the total weight of the melons that we have in that box. And you would also want to know the mean of the melons weight. This is length is wrong, it's weight. So the mean of the melons would yield 3.5. This is really handy for statistical operation and for data analysis. For example, R also lets you do comparison calculations. So your boss would ask you, I want to know which melons weigh more than 4 kilograms. And you would call just melons greater than 4, and this would yield a new vector, a vector with false, 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 true. Why is the fourth element true? Because this is the only one that's above 4 kilos of weight. And you can clearly tell him, oh, it's the fourth one. Imagine, this is really cool because just by applying this expression, R knows that this is a vector and returns you the same object that you have given him with the condition applied. Also, you can use the same logic to find melons that would weigh exactly 3 kilograms. So if you applied melons equals 3, this would yield false, false, true, false. Now, why do we have equals 3 and not equals 3? I'm going to give you a second to think about this. Well, it's because equals 3 would be an assignment. We would be assigning the value 3 to the variable melons. So equalities are represented with double equal. So that's the justification why we would have to do equals 3 and not equals 3. And or operations are also possible in R. For example, if your boss would ask you which melons weigh exactly 4 kilograms and 3 kilograms, you could do melons equals 4 and melons equals 3, and this would obviously, it would yield false, 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 because it's impossible for a melon to weigh 2 weights at the same time, right? So which melons weighed exactly 4 kilograms or exactly 3 kilograms? And we would use this pipe, and this pipe would basically just say the condition on the right or the condition on the left, where this ampersand basically tells you the condition on the left and the condition on the right. And this would now yield true for the third element on the vector, which is 3, and in fact it corresponds to the condition that we have applied here. Okay, but we have to watch out for some things when we are doing operations in vectors. For example, if you divide something by 0 in our either vector or an element or a number, you would get the symbol infinite. And when you have an infinite inside a vector, basically when you apply the calculation would yield infinity and not the calculation that you want to. This would yield 3.4 plus 3.1 plus 3 plus infinity. And this infinity would basically just ruin your calculation, and the vector will yield infinity. So we have to watch out for this. The same happens for nans, which are short for not a number. Nans are strange things that we ask R to do for ourselves. For example, imaginary numbers such as the square root of -1, that will yield a nan if you sum with a nan inside. And the same happens for not available in NA. If you sum vectors that have NAs, this will also yield a resulting NA. And NAs are pretty common in data analytics because there are a lot of columns where you don't have the whole information about everyone or every individual that you are studying, right? So you will have a lot of not availables, and you have to watch out for that. One cool thing is that R also lets us do this in most functions by using an extra argument in a function. For example, if we sum C with an not available here, and we use this argument na.rm equals true, which means remove the NAs from the vector, this would yield 9.5, which is the sum of the first three elements, and it would discard this fourth element. And also the same for the mean, so this is also a cool parameter that we can use. We are going now to go and dive deeper into the practical part, and thank you for watching this. I hope you're... Hello everyone, and welcome to this R programming course. So I'm excited to have you here. This is our first coding lecture, and in this lecture we are going to use R as a calculator. So let's first get a bit familiar with the environment that we have, that is RStudio. So here on this part we have the script file, and in this case the script file is where we are going to write our code, and our R code can be executed in multiple ways in the script file. We'll see how in a minute. And down below we'll have the console. The console is what enables R to understand our coding. We've seen this when we've installed RStudio, but we're just reviewing it so that you can get a multiple exposure to this concept. Okay, so in this console, we can see the output of the instructions that we put on the script above. So let's see what that means. First, just let me tell you how R interprets your code on this script window. So if we do 1 plus 1 as an example, this is a line of R code that we can use, run, and it will be interpreted on the console below. So if I hit Ctrl plus Enter when I have this code block selected, this will run and we can see here 1 plus 1 equals to 2. So the summing of these two numbers was done on the R console. There's another thing that we can do in the script window, which is giving comments. And comments to code are really important because they help guide the user or the viewer of the code if they have some difficulty on reading the code that's below. For example, here I'm doing 1 plus 1. I'm going to do a code above saying that I'm adding two numbers. So exactly below my comment, you can see what I'm doing in our code. So comments start with an hashtag. Everything that's after the hashtag on that line will be considered a comment and will not be interpreted as our code. All the rest will be interpreted as code. Okay, so now that we are using R as a calculator, we can do multiple things in here. For example, we can subtract two numbers. So if I want to subtract two numbers, this is easy. 10 minus 5, and we'll have 5, the resulting operation from this calculation. There are other mathematical operations or common operations that we do in our life, for example, multiplication and division. Let's see how we can do that in RStudio. So multiplication, you can use the asterisk to do a multiplication. And the asterisk can be written in R code in both ways, either using the asterisk from the keyboard or the cross that you have on a numpad that will enable you to do this multiplication. So 10 times 5, it should be 50. Recall that I'm running the command using Ctrl plus Enter at the same time. But there's another way to run code in RStudio, which is to select the code and then hit Run on this button. It's exactly the same thing, although I prefer the Ctrl plus Enter, that's faster. On a Mac, you have to enter Command plus Enter, which does exactly the same thing. Okay, let's aim for our other basic operation that we have here, which is the division. Division is also super simple. We just have to hit 10 divided with a slash by 5, and if we run this command, we have 2. And 2 is the resulting value from this operation, so it's correct, and we see that R interprets everything as a calculator would do, basically computing the real values of mathematical operations. Another thing that I would like to tell you is that R basically conveys all the mathematical operations that we are expecting. For example, parentheses. R also respects precedences between mathematical operations and the way that some, as the ones that are inside of the parentheses, are done first, then the latter that are outside the parentheses. As an example, if we do 10 divided by 5 over 5, the 5 over 5 will be computed in the first place, and the 10 over 1, in this case the resulting value from 5 over 5, will be computed in the second place. So it will not be 10 over 5 over 5, but 5 over 5 and then 10 over 1. Let's confirm that, and that's correct. So let me just add a comment here, add parentheses. Okay, so we've done how we can use R as a calculator with some basic examples. Next lecture, we are going to see how we can use functions to extract some numerical values. For example, how do we compute a square root? And we'll see that in the next lecture. Hello everyone and welcome again to this R lecture. We are back at our R as a calculator example, and in this lecture we are going to use functions for the first time. So functions are one of the most important components of the R language, and at the end of the course we will be developing our own functions so that we can transform some input into relevant output. So let's do here a function that calculates the square root of a number. R has already built in some function that you can use to calculate this, which is the sqrt function. So the sqrt function basically takes an argument, and this that I'm stating inside is an argument of this function. So most functions take arguments, as we will see throughout the course. Some of them don't, but a majority of them will take arguments. And in this case, sqrt basically takes a number, and the number is an arbitrary number that will compute a square root on. In this case, I want the square root of 9 that should yield 3. And that's correct. We see that sqrt, basically the abbreviation of square root, computes the square root of a number. We can do other mathematical operations using functions. So let's see exponentials. And if we do an exponential value of 10, we get the corresponding value. If we do the exponential value of 0, you know that we would get 1, because this is the value of exponential of 0. So again, R is complying with mathematical rules. Okay, so let's analyze one final function, which is the logarithm. If I come here and specify logarithm, I can use the log function to calculate any logarithm that I want. So let's compute a more generic value for logarithm. For example, logarithm of 1, which yields 0. Again, this is logarithm of base e. So if you want to provide another base to your logarithm, you can provide another argument to that function. And for example, let's see logarithm base 2 of 1, which is exactly the same. But if we change the values to 10, we'll see that our base will indeed change the value that we have inside the logarithm. So as you can see, my logarithm of 10 of base 2 is different from my logarithm of 10 of base e. Base e, it's the default. So we can also use these complex functions that we are using here inside other mathematical operations. For example, if I use a parenthesis to specify that I want the log of 1 times 10, this will obviously yield 0, because log of 1 is 0. And I can also do other stuff. For example, the square root of 9 times 10 divided by 10. What we'll do here is 30 divided by 10, because the square root of 9 will be applied in the first place. Well, this is not a good example because a parenthesis would be on the first place, so let me switch sides. In this case, what we are going to have is 10 divided by 30, which will be 0.3333. Let's confirm. It's 0.33333 and so on, because the square root is going to be calculated first before the 10. So bottom line, R really does obey to mathematical rules. Now, regarding functions, there's a cool hint that I want to show you. If you don't know the arguments that the function take, just use the question mark and then put the function after that question mark and run that code. You will see that you'll get a more detailed explanation of the arguments of the function here on this menu on RStudio. This is super handy when you are confused about the arguments that the function take. We'll do other functions throughout the course, so stay tuned and stick to the end. Let me know if you have any question regarding our materials and our programming. I'll be here on Udemy to support you.